Hi, this is lesson 28 in the use of JASP for understanding statistics. And today we continue to talk about planned contrast. This lesson is a direct continuation of the last two videos, especially the last one. So this is one where I really strongly suggest that you go back to the next one before you go to this one. But let's go ahead. We're going to go to our data library and pick up an analysis of variance. We're still going to be working with the data set on pain thresholds. I'm going to get rid of what comes up in terms of the descriptions and so that I can start anew. Very briefly, once again, we're looking at the effects of a factor, an independent variable called hair color on pain tolerance. And what we've been finding is that blondes tend to have higher pain tolerance than brunettes. And maybe there's some little bit of evidence that maybe light colored in general results in more pain tolerance than dark. But let's take a look at that. So what we've been doing is we've been doing an ANOVA, classical ANOVA. Remember that pain tolerances are a dependent variable. It's a continuous variable, a scaled variable. Hair color is a nominal variable. It basically is referring to the groups. Up comes the analysis of variance. It's basically showing hair color as the between treatments. It's the name of the between treatments or between groups. The dependent variable is pain tolerance is shown there. The residuals is your within group, and it is a significant effect. Last time we talked about the differences between, following up this ANOVA with a post-hoc test. Just to get that in focus again, I'm going to show here's our means with the blondes having pain tolerances of around 51, 59. For example, they might be able to hold their hands in ice water for 51 and 59 seconds, as opposed to brunettes, on the other hand, who hold their hand in ice water for 47 to 42 seconds, depending upon the exact coloring and what group they're in. And we've been focusing on, if you do not have strong theoretical expectations, you could do a post-hoc test. This controls for alpha inflation that comes about as a result of doing multiple comparisons. The more comparisons you do, the more your false positive rate is expected to go up. But statisticians have come up with ways of correcting for that increased number of comparisons, resulting in added error. And so these are conservative estimates that have been properly adjusted. But planned contrast, as we noted last time, are used if you have some theoretical expectation. So let's say that the main theoretical expectation that the researcher had was that blondes are going to have higher thresholds than brunettes. And the larger story is that lighter colored hair is an indicator of higher pain thresholds. So I can go in and do planned contrast with respect to that. And this is where we finished last time. Last time I took you through Helmert contrast. And in doing those Helmert contrast, I basically noted that the groups might not be ordered like you want them to optimize that Helmert. And so what you might want to do is do a custom contrast. But today what I'm going to do is just say, let's just start with the theory. And let's do a custom contrast to reflect that. So if the theory is that blondes have higher pain thresholds than brunettes, then I'm going to go in here and for blondes, go 1, -1, 1, -1. It doesn't show up until you click someplace else in the matrix. Click someplace else in the matrix, and here comes up the custom comparison, and it gives me a nice strong effect with a t-value of 4.48, probability value of P001. The estimate it shows is 30.50. Okay, so it's basically saying that, giving you evidence that blondes have higher pain thresholds than brunettes. What the contrast codes do, proper set of codes must sum to 0. And what they do is they basically say, for each group that has the same number, I'm going to treat those as one group. I'm going to average those together. It'd be like reorganizing your data and saying, let's just put all the blondes in one group and let's put all the brunettes in another group. It's exactly what it's doing and giving you a comparison based upon that. You can see that over here. Here I have the weights colored coded. So these are my contrast codes, or weights. And the way the analysis works is that you take those weights, you multiply them by the means. So 1 times 51.2 is 51.2 minus 1 gives you a negative. Sum those up, and there's your 30.5. The 30.5 is the estimate that you saw in that analysis. And what you're essentially doing with this set of contrast weights is you're basically saying, let's take these two groups, the 51 and the 59, average them together, that's 55. For the negative ones, let's take these two groups, the 42 and the 37, average them together, and you get 39.95. And then it asks the questions, are those two averages different? And what we found is that the averages are different. Notice that if I use the same contrast weights down over here, but let's say I started off with some mean and it didn't differ, then the estimate would come up to 0. Instead of the 30.5, it would come up with 0. Okay, so that's the way it works. Now I've done this contrast. Let's add another contrast. And this contrast that we're going to add over here, let's go ahead and do something different. Let's compare light against dark. So for the dark, I'm going to put in -1, -1, light 1, and 1. Click somewhere else, and this comes up with a t-value of 1.739, and the p-value is 0.103. Okay, not quite significant. So my primary interpretation is that blondes have higher pain tolerances than brunettes. Okay, now last time I talked about orthogonal sets of codes, and if you have 4 groups, there's going to exist 3 sets of codes that each give you independent assessments of what's going on. And the last code is kind of hard to see without a fair amount of training, but it is 1, -1, -1, 1. Click someplace else. Up it comes, and it is not significant. Now, for those people who have only done one factor ANOVA and are looking at this, what I'm about to say is probably not going to help you. But a lot of you have probably not only seen one factor ANOVA, but you have seen two factor ANOVA. And I want to point out that this set of contrast codes that I just did is basically the contrast coding for a two-factor ANOVA. The first contrast, what is it doing? It is looking for the main effect of blondes versus brunettes. The second contrast, what is it doing? It's looking at the main effect of dark versus light-haired individuals. And so what is the last independent question that you could ask? Is there an interaction between the light-haired and the blonde-haired on pain tolerances? Now, do you just want to take my word for it, or should we try and see if we can actually do that two-factor analysis? Let's go back to our data. Let's edit the data, and I'm going to go ahead and create new groups. I almost always use numbers, and that's what I've shown in my previous videos, but here I'm just going to go ahead and be quick about it, and I'm just going to note blondes are blondes. So blonde, copy, V, Control V, and everywhere I have blonde, I'm going to put blonde, and then brunette. Copy. Over here, everywhere I have light colored, I'm going to put light. And everywhere I have dark colored, I'm going to put dark. And to copy, I'm doing a Control C, then I'm going, and once I have that copy, I'm doing Control V to stick that in. I'm going to go ahead and name these blonde versus, we can do blonde versus brunette. And then click that. It didn't give me the apply options, but it did go ahead and do it. And then over here, I'm going to do light versus dark. Light v dark. It didn't take. Here, click somewhere else outside of that, and then it takes. And now when I click there, it says apply, apply, and now they're named appropriately. And now I'm going to go and I'm going to do a new analysis. You'll notice that I've set this up differently to where now I have two variables, two independent variables for blonde and brunette, and one for light versus dark. Two independent variables and one variable for pain tolerance. And so now I'm going to go to ANOVA, classical ANOVA, and it's taken me back to my previous one. I do want to keep that, but I want to do a separate one down over here. Here I can do a separate one. And this time I want to put pain tolerance as my dependent variable, and these two as my fixed factors. And it automatically models this as a two-factor analysis. There's my descriptives. It's the same means that I had before. And I want you to see, for my two-factor analysis of variance, I have a significant main effect for blonde versus brunette, with blondes on average scoring higher than brunettes. For the light colored, it is not significant. It's marginal for a very small n. I'd want to add participants, see if I can see if that is not significant with more power, because that's too few subjects. No hint of an interaction there. Look at those values, 0.001, 0.003, 0.706. They're the same that we got over here when we did the contrast. In fact, these t's, if you square them, square the t of 4.048, and down over here, you'll get 16.387. It's exactly the same. That's at a planned contrast, is exactly consonant with doing a two-factor ANOVA. Okay, so that's one more look at planned contrast. There's a lot that goes into planned contrast, but two examples there of kind of planning your theory versus simply looking at post hoc comparisons. And just one note, this problem lends itself to a two-factor analysis. I probably would have started it off that way. Not all one-factor analysis of variances can be reconstructed as two-factor analysis. And that's where the planned contrast comparisons really becomes useful, because you can get the power of a two-factor analysis of variance without having the completed cell structure that would allow you to do the two-factor analysis of variance. Okay, hope that helps. Talk to you next time.